started then. Hello and welcome. I look and I see before me a wonderful group of young people, all interested in computers and junk. And I hope that we shall have a good class together. It's very nice to actually meet all of you. So hi. I try to run a friendly classroom. Please feel free to raise your hand at any point during the lecture. Feel free to interrupt me if you don't understand anything. The whole point is that you understand stuff, so, you know. Yeah. So, if my memory serves me correctly, last time we were talking about, we'd gotten sort of through this material, we had just finished on what it means to be edge-aligned versus center-aligned, and we were just about to talk about like what the actual purpose of input capture is. So I thought we might review the slide on what input capture setup looks like, and then maybe that'll make more sense. Yeah? Good. So, I'm going to shut that off. Silence, fool! So, peripheral timers. We've been talking about peripheral timers for quite a bit. We only have a little bit more to get through, and then we'll be talking about interrupts. So, I hope everybody recalls from last week the setup of the peripheral timer. We have the timer counter itself, a register which holds the current timer value. We have the incoming clock signal, which is pre-scaled in the prescaler to produce a slowed down clock signal so that you can control the rate with which the timer counter increments, right? From that, we have the auto reload register, which contains the value that we either reload the counter at, or like when it reaches it, or when you count down to 0, this is what it resets to, 2 different functions. So we also have the compare and capture register, which does most of the work that is sort of programmer facing. In compare mode, we are waiting for the counter to acquire a certain value which is held in the compare and capture register. When that happens, we generate some kind of signal which is very configurable. In capture mode, what we do is we wait for an external signal to come into this guy. We then capture the current value of the timer, or the timer counter, right? By doing this, if you capture the counter at 2 different points, you can measure the difference in time between those 2 different points by subtracting one from another. Now, it might become a little bit more complicated than that if this timer has overflowed, but every time the timer counter overflows, either has an overflow or an underflow event, an interrupt is generated, so the CPU can keep track of the number of times the thing has overflowed or underflowed. If you multiply that by the maximum value of this counter, you'll get what the sort of true count value should be. Depending on how fast, depending on how you've configured the prescaler, you know, if you don't set the prescaler to do anything at all, you can have overflow events happening, you know, like in the sort of 100 microseconds to 1 millisecond range at sort of that frequency. But yeah. Oh, is there a mic in this room? Actually, can you guys hear me from the back? Is this an okay level of volume? I don't think I necessarily need a microphone then, but if I start getting quiet, let me know and I'll put one on, okay? Good. That's one of the benefits of like one of these more steeply, it's kind of like an IMAX theater. Have you ever seen an IMAX theater? Yeah. I really like those. Although every time I'm in them, it's like my brain. But anyway, so that's like your rough overview of what we've been talking about so far. So let's talk about the actual input capture process itself. So essentially, there are 4 different modes which you can use to time things, right? You can wait for a falling edge and then time from the falling edge to the rising edge. You can also do the inverse of that, time from a rising edge to a falling edge. These are both very important things to be able to do. You can also measure from one rising edge to the next, and you can measure from one falling edge to the next, right? You know, you probably could have pieced together that those are things that you could do. So this is how it works in association with the timer. Like the graphic that we started off on doesn't actually show you how or where the signal that you're measuring comes in, right? So this is how it works, right? So you've got the counter, and you've got the clock signal coming into the counter. You also have the external signal, which is coming into an edge detector. The edge detector, when it detects the particular type of edge that you're waiting for, which is, of course, configurable, it triggers the timer counter to be copied into CCR. It will also generate an interrupt, which lets the CPU know that there's a new valid piece of data in CCR. Again, we're going to talk about interrupts real quick. So yeah, there's only one CCR. Well, actually, no, that's a lie. You can have up to you can have as many as 4 of them, which can all be timing various things. So you can configure it quite a lot actually. But this is the essential thing to get, is that what you're doing is you're triggering a copy of the current value of the counter. Any questions about that so far? Question? No? Okay. Yeah, pretty straightforward so far. So one little point further, and then we'll talk about an application of this. So one of the things that you have to worry about is how clean your signal is. You should probably not assume that your signal is that clean. Sometimes, it depends on what you're measuring. Like, for example, going back to the last set of lecture slides, if you consider what the input from a push button looks like, you do have that mechanical bouncing, right? Which means you're going to get a signal that pops up and down a little bit until it reaches a rest state, right? So this is what this jaggedy part is meant to model. And if you're thinking it a little bit weird, that like the voltage level actually jumps up above 5 or whatever the baseline high voltage is, that's actually not as unusual as you might think. These types of things can sometimes be caused by like mutual inductance and electromagnetic interference. So sometimes you can actually see voltages that pop up a little bit over the baseline signal. But essentially, in order to sort of verify that you actually do have a low, like a falling edge, you can wait 2 clock cycles, 2 sampling. You can wait for 2 samples, and if both of those samples are low, then you have a pretty good, it's probably settled enough for you to count that as being the time, right? Make sense? Question?
What's an example of the external signal?
Well, if we get to the next slide, I'll give you a very good example of what an external signal could be, okay? Any other questions? Because we're about to talk about ultrasonic sensors. So, this is an ultrasonic sensor, if you've never seen one before. They're pretty cool. You've got a transmitting and a receiving speaker on them. So the way that an ultrasonic sensor works, essentially, is the transmitting speaker produces, well, ultrasonic sound. It bounces out into the room, reflects off of obstacles, and then the receiving microphone measures, it waits for the same frequency of sound to return to it. So with this, you've got 2 pins here which are important, right? You've got ground and VCC obviously, but you've also got a trigger line and an echo line. So when the ultrasonic sensor sends out a pulse, it also sends out an electronic signal over the trigger pin. When it receives the echo back, it sends an electronic pulse out of the echo pin. So if both of these are being read, then you can, actually, is the trigger, maybe you trigger it, maybe I got that mixed up. Well, at any rate, you can measure the distance between the trigger and the echo to determine how long it took the sound to reflect off of an obstacle and then back to the sensor, using this equation. So the distance is the round trip time times the speed of sound divided by 2. The round trip time is something that you measure. It's the distance in time between the sending of the signal and the receipt of the echo signal, or the wave, anyway. So speed of sound, at least in, sort of nominal atmospheric conditions, is 340 meters per second. So in the end, you take the round trip time in microseconds, you divide it by 58, and that gives you your distance in centimeters. So let's look at how this works electronically. Right? The echo pulse width corresponds to round trip time. So let's see here. Is that the last slide? That is the last slide. So the trigger signal, right? Let's say we have a trigger that's happening with 1 second between each trigger, right? So the distance of let's see. So the pulse width of the echo signal here, that's going to be proportional to the distance that you are from the obstacle, right? According to the formula that was derived on the previous slide. So we trigger the pulse, we then send it, and then we receive it back. And through that process, you can measure, you can get the exact distance. But of course, these are just signals. In order to actually be able to calculate that distance, you need to be able to measure when it starts, and you need to be able to measure when it stops, which means that this is the input signal to the timer, which you time the width of the signal, you time the width of that this pulse, and that gives you the distance, right? But it requires precise timing, because this, you're working on a microsecond range here, right? Which means that this happens too fast for a software timer to be able to deal with it. So that's why you need a hardware timer for this application. Any questions about any of that? Yeah?
If you have 2 ultrasonic sensors pointing at each other, can they mess with each other?
Oh yeah.
So with something I know, sumo bots, if 2 robots are both using ultrasonic sensor to kind of determine what's in front of them, and they're using the same frequency, I don't think it makes any sense. But can one trigger another's? I don't know how to explain, but
yeah.
You know what I mean.
Can the pulse sent by one be received by the other?
Yeah.
If they're looking for the same frequency of sound, yes. There's no way for it, there's no way for a ultrasonic sensor to verify that the pulse that it sent was sent by itself. If that's a weird sentence.
So how does that mean you configure which frequency your sensor uses? Or is it by default whatever the manufacturer mandated is?
The oscillator.
There is an oscillator on it as well, yeah. But well, I'll put it to you this way: this thing doesn't have enough pins to be configurable in that manner. So probably there would be a more expensive ultrasonic sensor that you could use with configurable frequencies. But you know, for a basic one like this, which I think, like, I don't know what these things run these days, but I know like 10 years ago these things were like on the order of 70 or 80 bucks. This one wouldn't be configurable. Generally speaking, like when you set these things up, right? You generally like try to not have them interfere with each other, right? You sort of have them give them non-overlapping spheres, like fields of vision. You try for that anyway. Now that's going to break down at a certain point, and like ultrasonic sensors are like, they're not the most reliable way of sensing distance anyways, because like if you have an object that's like perpendicular to the oncoming wave, then that's obviously going to work the best, right? But if you have something that's like thin and oblique, right? When the waves hit that, they're gonna like glance off it that way, right? And then it's not necessarily going to be reflecting much back into the ultrasonic sensor, so like something like that might be invisible to it, right? That's related to a problem that they had with the Teslas. You guys heard about that famous Tesla crash?
There's lots of them.
Which
Yeah. Well, the one where it hit, like the one where the car ran straight into the side of a transport truck. So what happened in that particular one? Like this was a Tesla self-driving car in autonomous mode, right? So the problem was that the truck was sufficiently shiny that it was reflecting the sky behind the car. So when the car looked at it, it thought it saw sky, but it didn't see sky. It didn't see that it was actually a truck because of the reflection. So it hit it, and at high speed. These are the sorts of things that we're still working out, but yeah. So ultrasonic sensors are like, they're pretty good, but they're not super reliable, particularly for stuff like that. They are probably better than they used to be, but yeah. Another way that you can prevent these guys from interfering with each other is stagger them. Test this one, then test that one, then test that one. Like pulsing all of them at the same time, probably a bad idea. You would want to do them one at a time. Any other? Yes?
Is the oscillator on the ultrasonic distance sensor, is that for the sound wave that's being transmitted, or is that for the timer?
That's an excellent question. I have only my own hypothesis because I haven't used one of these in a long time, but absolutely, I would say that is generating the frequency of the sound, right? Like, if you think about it, sound is an oscillating frequency, right? Where is that oscillation coming if not from the chip itself? And oscillators produce oscillating signals, and that's the only one you can see, so I would say it's a pretty sound hypothesis that guy in the middle is generating the sound frequency. Any other questions?
Battery's almost dead.
Battery's almost dead.
For the camera.
Oh, jeez.
That's off. Somebody's
Oh,
phone.
no. What do we do about that?
You can do it with like your phone.
I don't know how that's gonna help.
Yeah. Well, you can charge it off a laptop.
I do have a laptop.
Yeah.
Or someone brought you a gift.